So when we think about developing new data analysis methods for ISM studies, we nowadays think about machine learning and Bayesian inversion. What I want to show here today is that information theory can also be a source of very useful tools for ISM studies. So this is a work that was done by Luca Einig and Pierre Palu, but they couldn't be here today. So I will be presenting their work, and the slides are there. So the problem that we chose to tackle is the question of line selection or feature tracer selection when designing observation proposals. So when designing a proposal for observations, one has to make choices in terms of which tracers to go for, either in terms of which spectral setting to choose with the telescope or which telescope to choose, but also in terms of how much integration time you need to go after different traces. To be able to propose something rational, usually people use astrophysical models that relate the observable tracers to the physical condition of the environment. But most often those models are used by just taking the typical physical conditions we expect in the environment we are going to observe and checking that the lines will indeed be detectable with the observing time that we are planning to have. But the line being detectable is not the only important point. We also need the line to be informative about the physical variables that are of interest to us, for instance, the gas density, the temperature, or anything. So here our goal is to try to, from astrophysical models, be able to find the tracers that will best constrain the physical variables that we want to infer. And so this poses several challenges. The first one being that we need to find a way to actually quantify the potential of a given tracer to constrain a given physical variable. But we are also interested in more than a one-to-one relationship, and also at how a set of observable lines or any tracers, it could be dust continuum bands, how much information those bring on the physical conditions. So previously, there have been some approaches that have been tried. So the most naive one would be to look in the models at the correlation coefficients between physical variables and observables. But of course, physical correlation coefficients will miss anything that's not linear. We have proposed some previous approaches, but those relied on specific machine learning algorithms. And so they would only work if the machine learning method learned correctly and was able to fit the trend in the data. Here we are proposing a very general approach that relies on an information theory concept, the concept of mutual information. So in information theory, you can generalize the idea of entropy that we know in physics to any random variable. So for a discrete random variable, it's basically the same expression as in statistical physics, except it's not the same units, it's in bits. In our case, we will be interested in continuous parameters, so the physical variables, the line intensities. So this can be easily generalized into what's called the differential entropy. And the interesting point when you have physical variables you want to estimate and line intensities or other tracers that you are observing is that you can define a conditional entropy, which is the entropy. So the entropy for one variable gives an idea of how uncertain you are about the variable. For instance, it can be applied to a prior probability distribution that encodes what you expect about the variable. And then the higher the entropy, the less you know about the variable. When you move to the conditional entropy, it tells you how uncertain you are about the variable once you have observed a given tracer. And combining both of those by taking simply the difference between the entropy for the prior distribution and the physical variables minus the conditional entropy, so the uncertainty that remains once you have observed, you get what's called the mutual information, which is the information that the observable tracers gave you about the physical variable. So this is in bits, so it's a bit difficult to interpret the values, but to give a rough idea for a normal distribution case, gaining 1 bit of information is equivalent to reducing the standard deviation on your physical variable by a factor of 2. It gives a rough idea. Of course, in a non-normal case, it's a bit more complicated. So now we need to estimate this mutual information for astrophysical quantities. So the way we are going to do it is use models to predict the relationship between the variables and the tracers. And we are going to estimate this using a Monte Carlo estimation method. So we'll need to draw a lot of samples of physical variables and the corresponding line emissions. This is a bit tricky in terms of how to do this properly because naive estimators can be biased. So Pierre and Lucas developed their own implementation of this estimator. And to show an application of this, we are going to apply it to the case of observing PDR emission predicted from the PDR model, the Meudon PDR model, in the setting of observation with the IRAM 30-meter telescope, so observing molecular millimeter lines, sorry. So the Meudon PDR code that we are going to use models the physics of UV irradiated neutral gas, so photodissociation regions, where the UV field warms and destroys molecule at the edge, and you have a spatial structure, chemical and thermal structure. So the models solve simultaneously the radiative transfer, the chemistry, the thermal process, and the excitation of the tracers as a function of depth in the cloud. And from this predicts the observable line intensities that you can try to observe with telescopes. Here we are restricting ourselves to only 3 physical variables that we are going to try to constrain: thermal pressure, UV field, and the total amount of gas on the line of sight, the total AV. And because we will need to estimate the model for many different sets of values of the physical parameters, we are using the fast and accurate neural network emulator that was developed by Pierre Pallu in a previous work. This we need to combine it with an observation model, so a model of the noise that will be brought by the observation and the uncertainties that will be brought by the observation. So here we are simulating the settings that was for the Orion B large program, so an IRAM 30-meter large program led by Jérôme Petit and Marie-Vonne Gérin, which aimed at obtaining an unbiased data set for a full GMC. And so we adopted an additive Gaussian noise representing thermal noise with the same properties that were in this data set, as well as a multiplicative log normal calibration uncertainty corresponding to the properties of the EMIR receiver. And we keep the lines that would be observable in this setting, so roughly 33 molecular lines. So let's see what we can do with applying our mutual information tool to this setting. First, the strong points of this approach is that it doesn't rely on a linearity assumption. It can account for nonlinear relationship. It's not dependent on some machine learning algorithm and on the fact that this algorithm works well. This is a very theoretical estimate of the information that's present. It allows to estimate the many-to-many relations and not only one-to-one, so not just one tracer to estimate one physical variables, but groups of tracers to estimate simultaneously several variables. And it fully takes into account the noise model of a given instrument. And so from this, we can visualize the result in several ways. So here we are first focusing on the question of estimating the total amount of matter on the line of sight, so the total AV, from lines of CO isotopologues, 12CO, 13CO, C18, and lines of HCN, HNC, and HCO+. Here, what I show is that we can use this tool to show as a function of the physical condition in the environment where a given line will be most informative. So here the color shows the mutual information of the considered line with the total AV. And we see that, as expected, 12CO is only informative at very low AV because 12CO, the 120 line of 12CO will saturate when you have a larger amount of gas, so it will only trace the surface. And then 13CO and C18O become more informative as you are trying to probe larger amounts of matter. So exactly what we expect from our knowledge of ISM physics. And what we see here is that we can interpret those plots by looking. So those are just the intensity of the line predicted by the model as a function of the same parameter, AV and G naught. And we see that there are two things that contribute to a line being informative. The white line here shows the 1 sigma noise level of the observation. So of course, if you are in this region, the line is not significantly detected, and so it will not be informative. But then even when it's detectable, you need the line to be sensitive to the parameter you are trying to probe. And this is manifested in the fact that you need to have a strong gradient of this line intensities with the parameter of in question. And so, for instance, for certain CO, it is informative because there is a significant gradient in this direction, while 12 CO, because it saturates, is mostly constant as a function of AV, so it's not informative. We can apply this, of course, to the question of trying to probe the UV radiation. So it's probing a different part of the matter. It will probe the surface layer that's irradiated by UV. And we see that in this case, to the contrary, it's 12 CO that's informative because 12 CO will saturate. And once it's saturated, it will be related to the gas kinetic temperature and indirectly to the UV field that's warming up the gas. We see that for other tracers, it's a bit more complicated, and they are actually only informative because there is a strong switch in chemical regime when you go from very high G naught to lower G naught. And so they can be informative in telling you in which regime you are. So that was the first application of this method. But what's interesting is that we can consider the interrelation between different tracers. And in particular, the fact that different tracers could be redundant, in which case there is no need to observe both of them, or they can be complementary, and observing two of them together will bring new information. So here, what I show for each row is the information brought by one molecule, by one line, another line, the maximum of the two, and then the combination of the two. And so in some cases, we see that we don't gain so much by combining both of them. For instance, in this case, 13CO is a perfectly good tracer, and adding the 2 to 1, 13CO 1 to 0 is a perfectly good tracer, and adding a second line doesn't bring much information. But in some cases, for instance, these last lines, we see that 13CO 1 to 0 and C18O 1 to 0 both were not very informative at very high AV and very low G naught. But the combination of the two, so the gain is actually, there is actually a gain to be had in this corner. So sometimes lines can be complementary. Another way this tool can be useful is trying to see how informative the line will be as a function of the integration time. So here we show for different lines of different molecules. Here on the left as a function of the signal to noise ratio. So as expected, we see that at low signal to noise ratio, none of the lines are informative. They become informative around the signal to noise ratio of 3 or 4 or 5. And then, of course, they will saturate because at some point, observing longer doesn't bring anything new, but the level is different because some lines are inherently more informative than others on the parameter. And so here, it's not very interesting, but once you translate this into integration time, of course, different lines will require different integration time. And here we are comparing to the integration time we had in the Orion B project. And we see, for instance, that we wouldn't gain anything on HCO plus by observing longer, but we would gain information from HCN and HNC. And finally, you can use this mutual information to, among a large number of potential tracers, find the ones that will be best to observe a given environment. So for instance, if you know that we are going to observe filamentary gas, here are the results. And we see that the best tracers are 13CO, HCO plus, and C18O. And we, yes. And for denser, higher AV line of sight, we see that the order inverts, and C18O, as expected, becomes a better tracer of the column density. And you can look also at pairs of lines. Sometimes the best pairs of lines are just pairs of the best individual lines, but sometimes some lines that were not very good individually appears in the best pair of lines because they are very complementary to another line, and they bring information that was not present in the other line. So I'm going to conclude. So what I want to emphasize is that the method we developed is very general. It can be applied to any astrophysical models, any tracers, not necessarily line emission. It could be a continuum, dust continuum bands, and any telescopes, as long as you know the noise model, the corresponding noise model. There was no limiting assumption, contrary to previous approaches. And another interesting point is that this method can actually also be applied in a model-independent way, directly on an observational data set. If you have, so for instance, Luca is working on applying it to the Orion B dataset. So we have the Orion B dataset for molecular emission lines. We have physical conditions derived from Herschel dust observation. And combining the two data sets, we can look at the mutual information between the lines and the physical conditions without relying on an astrophysical model. I will stop here. And all of the tools that we developed are available. So the main tool is this one that provides a way for any model to compute the mutual information between parameters and observable quantities.